Germany is ready?
Okay, yeah, start.
Okay. Hello everyone, my name is Paul. I'm a member from Germany and I'm going to introduce you problem number 9, the candle in water. So the task was to add some weight to a candle such that it barely floats in water. As the candle burns, it might continue to float. Investigate and explain this phenomenon. So therefore I split my presentation into several parts. I would start with some properties of candles, then I'll give you a basic explanation about the phenomenon. And after that, I want to talk about big and small candles, and in the end, I will give you a short conclusion to it. And first, the properties of candle. As you can see, there are several types of candles. So there are pillar candles, tapers, and ear candles, made out of different ways of production and made out of different materials. So to make good physics and to provide good measurements, I decided just to pick one type of candle made out of one material, so that my measurements are as comparable as possible. So I took pillar candles with pressed wax made out of paraffin. So I choose that candles because AWA Katzen, it's a local candle producer, gave me the information that over 90% of the candles in the world were made out of this material, and they produced me that candle. So I had hundreds of candles made out of paraffin with equal density, equal material. So I had perfect candles for investigations. So now I will come to a basic explanation to this phenomenon. So at this point, I want to distinguish between small and big candles. So a small candle will burn on fully surrounded by air, where a big candle won't burn down fully in air. So the border between those two is around 5 centimeters of diameter of the candle. Okay, so now we look to the combustion in water. So this is where it gets interesting. So a big candle in water usually burns down as it burns down surrounded by air. Except that the well is a big, the border of the well is bigger, of course, because the cooling is high. Where a small candle will form a well underwater, but not above the water surface. There's just a small part of paraffin that melt and then burn as well. So at first I want to speak about the big candles, since they are a bit easier to describe. So the condition for floating. So what are the conditions that a big candle float? So we add some weight to the candle, such that it barely floats. So in my opinion, barely floats means that the density of water equals the density of the system candle plus added mass. So this is my starting condition. So since we light the candle, these two parameters, so the mass of the candle and the volume of the candle, are going to decrease. So now we could describe the total density of the whole system with this equation. Furthermore, the condition for floating now is that this total density is equal or smaller the density of water. Okay, so let's talk about some assumptions. So for large D, we could assume that the well is a cylinder, and we could also assume that we have a constant combustion rate J. Okay, so R over the time, as you can see in this little sketch, will become constant, and we expect Y over the time being linear increasing. Okay, and now we could determine this x over the time, so the part which the candle is outside of the water. So x over the time could be described with this equation now, so J is the combustion rate times T, so this is the mass loss divided by the density of water, and divided by the area, so the area of the candle, bottom area of the candle, and this should be x over the time. Okay. To describe the candle's behavior, especially for R, the radius, and the depth of the well, there is a paper of Mr. Theodorakis and Mr. Astigou, and they describe this behavior for small t at the beginning when we light up the candle. So, to show you the few some of the assumptions they did, so they said that there is a linear diminishing heat flux from the candle, starting from the candle. So, they give us some equations to describe it, but there are as well some problems. I won't go there into detail because it's not my own theory. I just use it to check whether my assumptions were correct. So, because the theory isn't that good, because they just simplified this heat flux and the horizontal heat flux, and they adapted the vertical heat flux just to fit the measurements. Nevertheless, they give us some equations for r over the time and y over the time. So then I did some measurements over the radius of the well and the depth of the well y. And as you can see, it fits quite well. And my assumptions were also correct for large t. Y is going to be linearly increasing, and r over the time for large t will become constant. Then I tried to figure out whether my assumptions or my basic theory for x over the time is correct, so the part which is outside of the water. Therefore, I measured the combustion rate with this setup. So I had a container filled with water via construction that the candle keeps in the middle of my container, and the force sensors in the data collection. Here you can see my measurements. So this is the time. On the y-axis there's the mass, and here you can see the mass lost over the time for two candles. So this is a candle with a radius of 5 centimeters, and this is a candle with a radius of 6.8 centimeters. Then I measured as well x over the time, used the video analysis, and you can see the results in here. So this is x in centimeters, and this is the time in minutes. And here you can see as well the smaller candle and the bigger candle. And now I try to compare these two values. Due to my theory, I can now describe x dot, so the duration of x, with j, because all others are constant. This is the diameter of the candle and the density of water. So these are now my two measurements, and I calculated, or I extracted now the combustion rate out of this. So the combustion rate was 6.77 and 6.06, and I determined x dot, which was these values, and then I tried to describe x dot with my theory, and as you can see, there is a big deviation between these two. But I have to consider that there is water evaporation, and since I was doing these experiments on 2 different days and had different water evaporation, my values between theory and real experiment fit very, very good. Okay, now let's talk about the smaller candles. Smaller candles are getting a bit more complicated because other things become important. So now I would start with some forces, because now it's easier to look on forces in this case. So we have, on the one side of the equation, we have the gravitational forces. The gravitational forces of the added mass and the gravitational forces of the candle itself. And then on the other side, we've got the buoyancies. So since I assume the density of the added mass is very high, the buoyancy of the added mass is almost negligible. And then there is the buoyancy of the candle, and of course the buoyancy of the well, because the well is very important. But even more important for smaller candles is the surface tension, because now the surface tension becomes a very, very important factor in this case. So now let's go to more detail. Why becomes surface tension so relevant? So this was my condition for floating, or the basis for my condition of floating for big candles. But I got some very main issue in that for the small candles, because as you can see in this diagram, where I measured the volume of the well over the time, that the volume becomes constant. So the well has a maximum volume for my small candles. So we would assume that the density will go to the density of the added mass because paraffin is burning. But this doesn't happen. At least the total density becomes higher than water. So we would assume, or we would expect, that the candle wouldn't float at all. But there is surface tension, as you can see in this picture. So here you can see the layer of paraffin which surrounds the candle, and that makes the candle able to float even when the previous condition for floating wasn't fulfilled. And yeah, let's talk about a bit more in detail. So here you can see a few other pictures of this problem. So, and now we have to say that there is a maximum force that can act due to the surface tension. You can see a bit in this photo that here is the candle and this is the area around. And when this difference between gravitational forces and buoyancy forces becomes too high due to the burning of paraffin, when this difference becomes too high, then the candle will rip off at this point and sink. And you can see this for example, in this diagram, where the mass over the time, and there was always the same delta M I could reach for this type of candle. And this worked as well for my smaller candles, for my bigger candles, smaller candles in this case. So I had always the same delta M I could reach before they rip off this surface tension ring, I call it. So this was always around 9.5 gram delta M. So this was the maximum the candle could burn. Okay. So since I wasn't sure whether my researchers were correct, I took some other candles just to prove it with another density which was much higher. So I tried to reach a fully burn of the candle. So as you can see here, this is another candle, and when the candle, the starting mass is lower than the maximum mass which was reached in this case, this is just photos, then the candle will almost burn fully down. So there's just a little well remaining, and due to cooling, the candle flame isn't able to melt any more paraffin because the cooling is so high. Okay, so now let's conclude the things a bit out. So for the big candles, which I define as when there is a well remaining, or a order remaining when they are combusting in air, they have Y/T linear increasing for big T's, as well as X over the time is going to be linear increasing since the start of it. Small candles, which I define that they burn down fully in air, have a constant Y over the time, constant X over the time, and the volume of the well also becomes constant for big T's. And there is no complete combustion when the mass of the candle is bigger than the maximum delta M I could burn. Thank you for your attention.
Questions from the opponent now, please.
Can you show us slide 5, please?
Slide 5. Yes.
So all these candles have the same material, right?
Yes.
Why is it so much higher?
And the combustion rate is depending on the wick. So the wick isn't exactly the same, almost the same.
Okay, well, I'm sure because I see 5 point.
Can you speak as loud?
Oh,
A bit.
I see 5.62 and 3.73. Those are very different.
Yeah, because of the wick. The wick is very important for the combustion because the wick basically is the reason for these different combustion rates.
But the smallest candle and the biggest candle have the almost same combustion rate.
Yeah,
If weight is that
it's just it's just because of the wick.
so does the rate change? How does the rate change the combustion rate?
Yeah, because when the wick of the candle is
I don't see like does it increase? How does it change?
when the wick of the candle is bigger, so the combustion rate obviously is bigger. But in candle production, it's important to consider a good combustion of the paraffin, because otherwise the candle will smoke, and this is not good for health.
Can you show us like 70?
17, okay.
So the line below is very current with the headings, but the line above that was very different.
Since I was using very, very sensitive sensors, and I had, at this day, I was measuring this one, I had very hard disturbances, so they measured these disturbances. Steps symbols.
Okay, I'm sorry, time is over. Thank you very much. You can continue the discussion after. So the time of preparation is almost over, and your time for completion stage is running now. You should start now because the time is running out.
Very well presented, that was approach, but especially I'm not sure it was acting that really well explained.
Loud.
I think how they experimented was not very well explained, how they added the weight, for example. But in general, the presentation was very well presented. Almost like 5, 6 dimensions, which was very good. There's
Okay, could we pause the time now? And could you try to connect to the beamer?
Connect to this one. You can connect to our.
And try to connect to the. Did you try to connect to the screen before? Yes. With the same computer.
Yeah, I've seen it work. We saw it work.
experiment was underrepresented as you explained it very well, but you said small and big. You said small and big candles. You said there was you defined it well, but there was no limit value. And yeah, you didn't change to temperature of water, which could be a parameter. Yeah, using sensors was very great, but I didn't really understand how you measure the volume of the well, and well, it's advanced. Oh, and if you used more sensitive sensors, it should have been more accurate with the theory. And that's all.
Okay, thank you very much. Let's start the discussion. That's yours.
Do not make it more clear in your theory.
Okay, so maybe let's go back to my setup. So I think you need to come a bit more closer to see it because it's quite a dark sentence I use. And I used 4 sensors. And the problem is I had such a water container. The container was about 20 centimeters high and had a diameter of around 10 centimeters. Imagine that the amount of water is quite big, which is inside this container. So there was around 2 kilograms. And the combustion rate, or the combusted weight of the candle is around 10 grams, 20 grams. So when I will measure this over the time, I need very accurate sensors. But this is a very big mass I have to measure. So that made very many problems. And so I was using 4 sensors that were very accurate. But now, since I was using 4 sensors, I had 4 times the measuring error. And when there were steps on the ground, yeah, they also were measured. And I was measuring at my school, and this was a normal school day. So I had here a break, and exactly here a break in my school. And you can see these breaks very good because there is the standard deviation of my values quite high. And in this case, I was measuring at the weekend. There was no disturbances, and that's because the values were so good.
So, then you walk between 10 minutes?
No, days. Days. I measured these 2 on different days. No, I measured every second and made the average. And then I calculated the standard deviation from it, and this is why I have errors.
Those breaks are from.
So one point is an average point of around 20 or 30 minutes.
Oh.
30.
But in 30 minutes, there's always a break.
No, this is also just random, right? Yeah, there was a break. It was just.
In 30 minutes, there's always steps in that particular place.
You know, when they were breaking my screen. So when I had disturbances due to my experiment, and they were unluckily at a few points.
You said you made 30 experiments.
30 measurements. This is the average of 30 measurement points. So over the time, I measured around 5,000 measurements for each measurement, because that would be way too much for diagrams. I calculated every time the average of just a photography. So behind each point of that is the average of 30 other measurements.
Then how did you measure the burn volume of the candle? How did you measure the burn volume of the candle?
Okay, yeah, I measured it. Maybe let's go before I can show you. So this was quite a complicated measurement because since the well of a small candle will look like this, So I was using a scale, and then I put water inside of it. So until it was full. So I was burning 5 or 6 different candles. For each candle, 5 candles for each candle. I got the measurement because afterwards I put water inside of it. I can't use the candle anymore because the wick is full of water and the combustion isn't anymore possible. So I fulfilled it with water, and then I measured the weight of the water, and then I could calculate the volume of the water.
After the candle extinguishes sulfur, the extinguishes sulfur.
Yeah.
Did you wait for it to extinguish itself?
No, I did.
Okay, well then there is liquid perfect.
Yes, it
That's
is.
a solid price. Did you consider that?
Yeah, I considered it, and that's why the error bar is quite big. Since the density between liquid and solid paraffin isn't, the difference between isn't that big, it's around 780 kilogram per cubic meter for the liquid paraffin. For the solid, you saw it's around 870. So kilogram per cubic meter, it's a difference, but not that high. So that's why I calculated this error loss, plus the error I had due to this method.
And can you show us your experimental solution? Actually explain.
For what? For the X over the time and the part which is outside of the water. So I don't get the point clearly. So just tell me which slide number or which. So you mean this or? Yeah, I already explained this. Maybe let's go to this part. Here it was for me. I could use a bigger container since I doesn't want to measure any weight of the candle. So I used a bigger container, and there was the candle, and you can barely see this ring around it. There's a wire construction because due to surface tension, you could imagine or expect that the candle will move to the borders of the container due to surface tension. And that's why I had a wire construction. And maybe I can show you another picture. So here you can see this one. This was the wire construction for the smaller container. I had here the wire. The wire was always under the water surface. So I can be sure that there wasn't any influence of the wire construction when the small candle still this paraffin layer on the water, on the top of the water surface. So it was underneath it, and it guarantees me that the candle will reach the side, because when the candle will reach the side, the candle will sink earlier, because there isn't such a good cooling anymore, obviously, because there isn't no more water.
Are you sure it doesn't affect
No.
it touches the
Yeah.
solid touches solid?
Yeah, there is a friction, but since the movement of the candle is so slow, you can neglect the friction.
Well, for the tin or small candles, you talked about surface tension. Did you change the surface tension to make sure that it doesn't depend on that?
I was changing the surface tension. I put in some washing liquid so that the surface tension is drastically reduced. But I could observe that the candle still keeps on floating because the layer is so big, and the only reason for the fact that there is a maximum delta M I've shown you is, give me just a second, I will show you one. Maybe you can see it better. It's not that the whole candle will sink. You can see when the candle sinks, this layer remains because it rips up at this point. This point couldn't hold the candle in. It just isn't strong.
If you add this version,
Yeah.
and it's still floating,
Yeah.
are you sure that surface tension
Yeah.
actually acts on it?
Yeah, because this area is so big that there is no difference how big it is.
After the explosion itself. The area.
No, the candle just burns. I added some washing liquid.
Which area is it?
The area of this paraffin layer on the top is so
When
big.
did you add the
So the candle will float at the beginning anyways, and then it forms this kind of thing.
But I think before it formed this, which I should prove.
Yeah.
Yeah. So it continues to float.
Yes.
So the area is not floating because the area is not formed yet.
But the area forms, and it's no surprise that the candle
There
floats.
must be a time.
This forms in around 10 minutes. Very early. Very early. After 10 minutes, very.
I'm just asking before this you add filter detergent, it's still floated. Yeah.
At the beginning, yes. And then
Yeah.
immediately this was formed.
But in 10 minutes.
So yeah, in 10 minutes it was that big.
Alright. I am asking, how does the superstation even before it is
Because this area is so high, so it doesn't depend on the surface on the surface tension of the liquid. That considering which liquid I put there in the water. So that's because of the very big area I have. The force is even strong enough when there is this washing liquid inside.
to measure superstation?
The force. No, I didn't measure this because it's quite complicated and difficult. As you could
Okay, I'm sorry, the time is over. Thank you very much for the discussion. You still have 1 minute to sum up there.
Okay. Well, we talked a lot about surface tension and how the measurement volume of the well. He answered actually very well, but some parts of explanation is not present in the presentation. And of course, the theory lacks surface tension, which I think you put a lot of importance to. There you go.
Okay, so the first question is for the reporter. How long did you conduct your experiment?
how long it takes?
Yes.
In the day, I showed you around 3 hours.
Sure.
Or depending on the candle, I use smaller candles, just run for around a half an hour.
Then what happened if you conduct experiments for a longer time?
Yeah, so for the big or for the small candles? For the small candles, I could observe the ending of the whole process.
You mean
For
see
big- for the-
it will still fall on the surface?
depending whether the starting mass was bigger or smaller than the maximum mass. And for the big,
Bigger than small.
I mean when the mass of the candle at the beginning is bigger than this critical mass I showed you in the experiment. For the bigger candles, they burn for many hours.
And then the next one is how significantly does the surface tension of candle come down?
For small candles,
Do you have a value for it?
I have no specific value because it's complicated to measure.
Ask how the value.
The value has to be much bigger. So with a big factor between the big candles.
Thanks. For your opponent, do you think there's a way that we can calculate the surface tension?
I don't really see it.
Okay. And also for a reporter, how did you add mass to reach their limit?
I added a couple wire.
Okay. And how do you know the boundary between the big and small candle? Do you do it experimentally?
Yes. I observed it due to my large candle range.
Can you please change your slide 21?
21, yes.
Thanks. We see that there are some oscillations in your data. Then what happened?
And for this, it's just an error because the candle sometimes moves a bit. And since I was using video analysis and the load is constant,
Then for your opponent, do you think there's any reason except for the errors for this oscillation?
Well, I have only this explanation that says.
Okay, thanks. And you mentioned that you use wire to make sure it is in the center, the candle does not touch the container. Then do the candle is against wall? Do you think that the candle touch the wire will affect?
No, it has no effect but it touches, yes.
So
But it has a solar small effect that I can do.
You think because to not see?
No, I don't think it's because, I don't think that this has any effect on the sink or not sink.
Okay, then also for reporter, do you think there's any situation when the candle will sink?
Sink in which concrete situation?
On
Yeah, you can.
for
I
example,
showed it you. I showed it you in the report for small candles. When they rip off
what
this,
about big candles?
for a bigger candle,
Yes.
I observed it after a very long time when the candle was rotated due to disturbances.
Okay, thank you very much. Thank you very much. Time's over. 2 minutes.
要哪个没有的那个？
Yeah, it will be easier to place it after. No, it's not bad.
Did you see that?
How long are we in Taiwan in the water? So I believe the method here is what causes the candle to float, and what are the conditions necessary to observe this phenomenon. For the purpose of the first, in the observation part, they have been candle wandering, but they don't have been wandering qualitatively. And for the theory, they have a clear definition, and for setup, they measure well on those dimensions, but the candle position is not controlled very well, and also the wick is not controlled. And for experimental part, they have also met candles, which is quite good, but not time for those big angle experiments. And for the conclusion part, they have comparison with the theory and what is only qualitatively explanation. And for experiments that points out some uncontrolled weak properties and other as well experimental details, which is quite good, but they did not attempt to clarify some comparison between the theory and experiments. And for instance, the opponent asks about the measurement of the mass, and the opponent thinks due to the disturbance near sound isolation or areas due to the disturbance near the experiment control. And the rule suggests that the variance might not be constant, and we should test more on it, and the assumption might be incorrect. And next, the opponent asks about that how do you measure the dimensions, and the opponent said that they use water to fill the candle well and also measure the volume of the water. And the rule thinks the thermal expansion of the paraffin is extremely high, so leads to some underestimate of the volume. And also, candle weight is not considered, so there might be some error, and which might be some significant for a small candle. And also, let's talk about the position of the candle. And the first thing, the candle is moving, so there's friction, but candle won't touch the wall. But the the candle does touch the wall, which might affect the phenomenon. And the candle movement might cause error in the lens measurements because of the camera. And then also talk about the area of paraffin, which is relative to the surface tangent. The reverse side did not measure the surface tangent, and the reverse suggests that it easily measure it by finding the circumference of the wax field and also mixing an additional volume force from the cavity. And for example, we asked the reviewer asked about how long was the experiment conducted, and also saw the calculation of surface tangent and the cost of the oscillation. For some point missed, first we think that the time scale for his experiment is not long enough. We suggest that maybe he can increase the length of the candle, and thus you can observe for a longer period and see some other phenomena. And also there's no quantitative comparison of the surface tension, which we think this additional force match experiment, and also the candle can still float beneath the surface of water, which is caused by surface tension and should be calculated more detailed. And also another point is the buoyant force calculation for the small candle that did not include the additional cavity on the top of the candle, and this will also be considered. And for the position of the weight, that this will will cause some large candle to sink, which then did not investigate enough on the sinking cast. And also the heating of the water, the distribution, and the total distribution are not considered yet.
Thank you very much.
Okay. So,
Concluding remarks.
yeah, now some concluding remarks. At first, I want to thank you for this great exposition, this great review. It was a very pleasure to be in this fight. For some points I want to talk about is, yeah, you told me about the added mass in the discussion, in the questions, and yeah, I think this is a point we could discuss in the presentation. It was quite full, so I think I put out some parts that are obvious, in my opinion, and so it would be better when this is in the discussion a very big one. Then the opponent told me about the accuracy of my measurements. I think due to my explanation and due to the data I showed you, that they were quite accurate, as accurate as possible for my setup. Then there was a discussion about the surface tension, and I want to put a bit of remark on this, because the surface tension for the small candle is really relevant, but the force due to the surface tension is not as much connected to the surface tension of the liquid itself, because there is such a big area. So the surface tension of the liquid becomes lower due to adding some other things to the liquid. The force due to that is still high enough due to the big surface of this paraffin layer that the candle will keep on floating. And we discussed very much at this point, and the discussion wasn't finished, and there was no conclusion at this point, and I don't like this point, especially. So then the reporter told me about the wick, and that I should have changed that. And I have to say that this is very complicated. The wick is very important for production, and the candle producers have very to take focus on this point, because the wick has to be such big that the candle won't smoke, and smoke is very dangerous for the human's health. And so I wasn't able to change it, and this is a very, especially dangerous point for me to change it. Very hard to make. So the combustion rate I also assume as constant, as you can see in these measurements. I explained the deviation to the small oscillation. So thanks.
Thank you very much. Questions, please.
Okay, I have a question to the reviewer. Will you please tell me that is the length of the candle? You asked the length of the candle. If you change the length of the candle, then you will see the different results. So it's really the length of the candle. Do you think it's matter?
So, but it's important to change the length of the candle. The length of the candle, whether it's an important part here.
Oh, I think that will burn for a longer time, so we think there's might be some other situation.
Okay, thank you, Artem.
Question to the reporter. Can you actually say the parameters determine your candle to be big or small?
And as I said in the presentation, the border I could explain quantitatively when there is a well form, surrounded by air, and in numbers, it's around 5 centimeters of diameter, especially for my candles I use.
But if you change the parameters of your system, for example, the temperature of water, does this radius changes?
The radius of the world changes, but my definition not.
Okay, thank you much. Can I see the slide number 17? Yes, back again. I have two questions. The first one, you said every point is somehow an average of 30 other points.
Yeah.
So then, if it's an average, my question is how it's possible that the error rates it's the same for all the points?
Because the error calculated was for the whole thing, the standard deviation.
But if you get an average of 30 points, there is a standard deviation of that average.
Yeah.
How big is that one comparing to this error here?
For some bigger, for some small. For these ones, it's obviously big.
Okay, and my second question connected with that one. So this is in minutes.
Yes, it is.
So say like this peak lasted like 5 minutes.
Yes.
And you said it's due to steps.
Yes.
I don't really get it. Like this means that it's a difference of roughly a few grams.
Yes.
Which lasts for something like 5 minutes.
Good. I just assumed it to be at my school that there were many steps. So this could be the error on this. So the measurement with verification, I saw that it was not constant. So this was just my assumption.
Okay. Some time?
So I have the same question, like you partly asked it, but like my question is just, is this a single candle and averages over 30 consecutive time steps, right?
Yes.
Okay.
When I'm able to comment on that, what also could be possible, since I was using 4 sensors, and I calculated, and I added all masses or forces I got when the candle was moving due to the steps, it might reach another sensor, a sensor which isn't that accurate, and this might cause this peak, because it reaches for around, let's say, 5 minutes, another sensor, the edge of another sensor, because there were 4 in this. When it reaches this sensor and then goes to this one, there might be another change. So this might be the explanation for these longer, higher peaks you can see here. But you're correct, this could be the number.
That's still some time for questions. If there's no one else, I still have a question to the opponent. You discussed for quite a while the surface tension, and did I get you correctly that you replied on the question of the reviewer that it's not important, the surface tension?
Maybe for the small candles, but I was mostly asking about why didn't they measure and how. I think he didn't really explain well how it affected and why.
May I comment on that?
Yeah, sure.
Yeah, that's good. I was thinking about how to measure this force, and since this force is very, very low in value, so not very low in comparison to the other forces, but in value it's very low. So there is simply no possibility to measure this in a quite good way without a big measurement error, I think. And that's why I want to explain what I think is important, explain it qualitatively and not in quantity.
I have one question.
Right.
So you said you gave the comment that some points in the presentation are not correct. Yes, you gave the comment that in your conclusion that some points of the reporter is not correct. Can you specify or have you pinpoint which point is not correct?
Very briefly, so where he was not correct with his presentation?
I meant like especially that part.
Okay.
17, yeah.
Okay.
And the fact that he didn't measure.
Okay. Okay, thank you. Time's over. So we have time for Rev. We are ready? So, grades for the report. Okay, your grades. And now, I start reading from Frida. Frida, you don't touch the red ones, you just use the blue ones. Okay, so it's an 8, 6, 6, 7, and a 5. Thank you. Prepare the grades for the opponent. And grades for the opponent. Now, oh, that's fine. You don't use the red ones. Just use the blue ones.
No? Okay.
Okay. So it's a 3, 3, 3, 3, and a 3. It's a dream of 4 chairs. not the value, but the strength. And now the grade for the reviewer. Now, 7, 6, 7, 7, 6. Thank you very much. Okay, so we had, probably the largest spread was for the report, and it was between 5 and 8. So I was on 5 from 5, so it was like could have been 6. Basically, I had a big issue with the measurements of the weight, because like the steps, even if you have like some oscillations which are like in the frame of pulse, which were caused by steps. They certainly don't use oscillation which have a time frame of like 5 minutes or something like that. So probably like maybe your statement which you posed at the very end would have solved the problem, but certainly this is something which scientifically you had to research on, because the change was pretty high comparing to what was your like final result. So this was like a rather major issue scientifically from my side. And also the second thing where I had like issues with the physics, that on one side you stated that like you need the surface tension because you have this discoveries with the small cannula, but then you said the value of the surface tension is not important at all. But if it's not important at all, then it can be zero as well, and then you don't need it then there is like no effect of that. So these were basically like the points which made me to go down like so I had 2.5 for presentation and 2 points for discussion. But Farida, you'd like to report?
Basically, I gave the A because I found that the level they like the mathematical model. I like their mathematical model. They explain their parameter in a very good way. And the very good thing is that they attain in every stage by in performing the experiment. So they attain their equilibrium position, which is very good. I like, though there is some deficiencies, but I was thinking that in my opinion that is the good at this level. This is the good.
Okay. Thank you very much.
Considered very good.
For the opponent, it was like extremely smooth, but it still would be nice if anyone would like to comment anything. Or I can do that as well. So I gave you 0.5 for the questions, 0.7 for